Welcome! Today we're going to dive into a really fascinating and kind of radical new way of looking at the universe. It's called the Geometric Scaling Framework, or GSF for short, and it suggests something pretty wild. What if all the weirdness of quantum mechanics isn't weird at all? What if it's just the natural geometry of reality, but a reality with an extra dimension, the dimension of scale?
So let's just jump right in with a really basic question. You know how the world seems to have, well, a split personality? The world we see, bowling balls, planets, you and me, it all follows these nice, intuitive rules. But when you zoom way, way in, down to atoms and electrons, the rules completely change. It's all bizarre and quantum. So why? Why the two sets of books?
All right, so here's our game plan for this explainer. First, we're going to talk about what I'm calling the physics of zooming. Then we'll look at the classical illusion, how we usually explain our everyday world. After that, we get to the really cool part, a new dimension called scale. We'll see how that changes everything, looking at what it calls reality's shadow and how it rethinks measurement as separation, not collapse. And we'll wrap up by asking, could this be a unified geometry? Okay, first up, let's really get a feel for this core puzzle, this scale ladder of physics.
Think about it like this. As we zoom in on reality, the language we use to describe it has to change. You start at our level, right? Classical mechanics, things you can see and touch. Then you zoom in a bit and you hit molecules and atoms. Okay, now you're in the world of atomic physics. But if you keep going, zoom in even further, you get to the wild world of quarks and gluons. That's quantum chromodynamics, or QCD. Now, the deep down laws of physics aren't changing, but our description, our effective theory, yeah, that changes dramatically at each step.
So how does modern physics actually bridge that gap? How do we get our solid, predictable world to pop out of that weird quantum foundation?
And here's the most important thing to remember. The standard view is that it's always quantum underneath. It doesn't just switch on when things get small. The real mystery isn't why the micro world is weird, it's why the macro world isn't.
Okay, so one of the main tools for this is a concept called decoherence. Think of a quantum system's weirdness, like an electron being in two places at once, as a beautifully clear ripple pattern on a pond. That pattern depends on all the waves being perfectly in sync, or coherent. But now imagine it starts to rain. Every raindrop, every stray photon, every little air molecule bumping into it scrambles those ripples. The beautiful complex interference pattern gets washed out. And what are you left with? Just a messy, averaged-out surface, which looks a lot like the simple probabilities of our classical world.
So physicists basically have these two big tools in their toolbox to connect the quantum and the classical. You've got decoherence, which we just talked about. That's how quantum effects get smeared out by the environment. And then you have this incredibly powerful mathematical idea called the renormalization group, or RG. It's basically a mathematical microscope for seeing how the fundamental forces and interactions themselves seem to change as you zoom in or out. But now let's get to the new proposal. Let's see how the GSF takes these ideas and puts them together in a completely new and, well, geometric way. All right, here we go. This is the heart of the geometric scaling framework. The formal definition sounds a bit dense, I know. A theoretical framework that interprets quantum theory as the natural dynamics of an object living on a manifold where logarithmic scale is a physical coordinate. Okay, let's unpack that, because the core idea is actually beautiful and simple. Forget for a second that quantum mechanics has all these weird rules. What if it's just geometry? What if zooming in isn't just something we do with a microscope, but a real physical direction you can move in? That's the big move here. We're used to thinking about space, X, Y, Z, and time. GSF says, hey, let's add one more coordinate. Let's treat logarithmic scale, which we'll call U, as a real geometric dimension of our universe. And if that's true, it means the most fundamental thing in reality, this thing GSF calls psi, isn't just at a point in space and time. No, it's a multi-scale object. It exists across a whole range of scales all at once. Kind of like how a single musical chord is actually made of many different frequencies all sounding at the same time. So if this big multi-scale object is what's really real, then what on earth is the wave function we learned about in class?
GSF's answer is just wow. It says what standard quantum mechanics calls a wave function is a rung-projected corridor amplitude. In simple terms, it's a shadow. The wave function we've been studying for 100 years isn't the real thing. It's just a projection of this deeper, multi-scale reality.
And why do we only see the shadow? Well, think about it. Our instruments, our experiments, they're all built to work at a specific scale. They're locked in. They don't have the ability to see up and down this new U dimension, so all they can ever see is a slice, a single projection of the true state.
This changes everything, even how we think about probability. In standard quantum mechanics, the Born rule, which tells you how to calculate probabilities, is basically just tacked on. It works, but nobody knows why. In GSF, it's not an extra rule at all. It's what naturally falls out when you account for the fact that you can't see the full-scale dimension. It's the mathematical result of your limited viewpoint.
Okay, this is where it gets really good. Let's see how this geometric picture gives us a whole new and much more intuitive way to think about the biggest puzzle of all, the measurement problem, or the collapse of the wave function.
So, you know that classic quantum effect, interference? It's how a particle can seemingly go through two slits at once. Well, in GSF, for two different possibilities to interfere with each other, they don't just have to be in the same place at the same time. They also have to be at the same scale. They have to physically overlap in this U dimension.
So what is a measurement then? In this picture, it's just an interaction that literally pushes the different possible outcomes apart from each other, but along the scale dimension. And as that separation in scale, that delta U, gets bigger, you can see right here, their ability to interfere just plummets. It decays exponentially. So the quantum weirdness doesn't just poof and disappear in some violent collapse. It just gently fades away as the different realities get too far apart in scale to see each other.
And that's the key takeaway right here. In this framework, collapse stops being some spooky, instantaneous mystery. It's just geometry. It's what happens when the different branches of what could be move too far apart in the scale dimension to interact with each other anymore. They don't vanish, they just separate. So, if you take this idea seriously, what does it mean for how we think about, well, everything? You start seeing all these foundational concepts in a new light. Wave-particle duality? That's not a paradox anymore. It's just what happens when you look at the same multi-scale object from different angles. What's a baseball? It's just a really stable pattern that's now so far separated in the scale dimension from other possibilities that it's locked in. Even something like a proton can be reimagined as a kind of stable, self-perpetuating knot of pure geometric energy.
And this leaves us with a really provocative question to ponder. We all know Plato's allegory of the cave, right? The idea that we might only be seeing shadows on a wall. So, could our entire three-dimensional world be just that? A shadow of a deeper, richer, multi-scale geometry that we're only now starting to figure out?
It's a pretty mind-bending thought, and the fascinating ideas we've explored in this explainer all come from the geometric scaling framework, which was developed by its author, Nader K. Hijazi.